Hi everybody, this screencast is going to be a discussion of the highlights of Chapter 5 regarding graphical interfaces and GUIs. And what I really want to look here is the architecture, the software architecture of what makes this special. And frankly, it's one of the big driving things that have made Linux and Unix as well pervasive in the marketplace and has contributed tremendously to its spread and its acceptance, both from a server and from a desktop point of view. So if we take a look here at this next slide, and this illustration is also in your textbook, we're going to look at the architecture of how all of the components of the graphical interface are built in layers, and these are layers of abstraction. So the following slides, I'm going to discuss each of these 5 areas, and we're going to work from the bottom up, from the hardware through the device drivers, through the X window services, to a window manager, and to the desktop environment eventually at the end, which is what you and I as users actually see. So let's start with this first layer with hardware. Obviously, this is where everything begins. Hardware is, of course, the physical components of your graphical interface. And this is really where the rubber meets the road, if you will. So let's think for a second about the hardware and talk about a couple things that we have to consider here in this design. GUIs are tremendously complicated and resource-intensive critters. So there are literally, very literally, millions of issues and tasks that have to be handled anytime you have a running graphical interface. Your software has to respond to, or the environment has to respond to, the specific terminal type, and I'm talking about the actual monitor, the video driver card, all of the hardware that's associated with simply with your display, resolution, frequency of refresh rates, where the pixels are, how the windows refresh, all of that stuff, as well as, of course, events, because this is all event-driven software. So we have a mouse to keep track of, knowing where the mouse is, what state the mouse is in, has a mouse up, mouse down, has an event occurred, something being clicked and dragged, has a button been clicked on, etc., etc. Windows being resized and all of that. So these things are all hardware specific. The actual physical operation of implementing them really depends on the hardware. So the first thing you want to be aware of at this point is that this is the thing that's going to change. Your hardware is going to change faster than anything, probably anything else in this world. Every 6 months, new monitors, new displays come out, new way of interfacing a mouse, the different kind of 1-button, 2-button, 3-button mouse, the Apple's iMouse, the super mouse that they have out on the newer machines. All of these things are hardware, and all this stuff is going to change. So that last point on this slide is that we really need to have an architecture that decouples as much as humanly possible from the platform, because the hardware changes constantly. So how do we start to implement this kind of a structure? Well, first of all, we do it in the traditional Linux, Unix way by having device drivers that are built into the kernel. Meaning that the only way anybody ever touches the hardware is through a device driver. That means that if you're any application layer above the hardware, the only way you're going to get to that hardware is by making a kernel call which contains the device driver, which will in turn direct the hardware. This is an absolute must, and this is a sacred piece of the architecture in Linux. Device drivers are built into the kernel. So this is, mind you, a hardware-dependent layer. When you get new hardware, your kernel has to support that hardware. Now that seems like a daunting task, and frankly, sometimes it is. However, for the most part these days, when a vendor comes out and builds new hardware, new mouse interface, new display adapter, new video card, etc., they're going to provide device drivers. There's some issues out there about whether they're open source or not, but for the most part, the manufacturers these days are releasing their device drivers as open source code. And even if they don't directly go out and say support the Linux 2.6.32 kernel, somebody out there in the Linux community, a device driver programmer, is going to grab this thing, he's going to look at the code, and he's going to develop a driver that works in that version of Linux. That Linux kernel rather. So this is the one place where there are some dependencies. But as I said, for the most part, when new hardware comes out and gets accepted, there's a kernel mod or kernel driver that is going to support that. Okay, so just to reiterate, the core concept in kernel design is what a device driver is. It allows the access to the hardware only through calls in the kernel, and it really is our sole layer of hardware dependency. This is a really good thing. All right, so how do we start building a graphical interface? Well, we have to have, of course, all of the primitive elements of a GUI, meaning the ability to understand the desktop, the ability to listen to a mouse, to know how to draw a window, know what a window looks like, know that it has a border, that it may have buttons, it may have a minimize, maximize, kill button, all of those things, all of those behaviors. Well, we do this through a layer of software known as X-Window. By the way, it's very common for people to mispronounce it as X-Windows, plural, but the proper name of this is X-Window. And your book the textbook discusses this in some detail and talks a little bit about the history. It is the single most important layer here, because this is the layer that was started to be developed in the early 1980s and has been alive and working well ever since. So what does X-Window do? It provides the low-level services for the GUI elements, as I mentioned earlier, knowing where the mouse is on the display and what events have happened. X-Window provides the ability for other programmers to call these widgets, these little primitive GUI components, if you will. There's no device driver code at this level. X-Window only calls to the device drivers through kernel calls. And it really presents the heavy lifting services, if you will. By way of metaphor, when I say heavy lifting, consider something simple like this. You have a backhoe, and you know that with a backhoe, you could dig a trench or you could dig the foundation of a house. A backhoe by itself doesn't know how to dig the foundation of a house. It's pretty stupid, but it can do the heavy lifting. It can pick up dirt and move it, etc. In order to build a proper foundation for a house, you probably need a couple of other things above that backhoe, so to speak. You need a skilled backhoe operator. You need civil engineers who are designing and providing the specifications, if you will, for the way that this foundation is going to be built. This is what X-Window, it's kind of like the backhoe for that, if you will. Hopefully that'll make a little more sense as we look at the layers above this. But it does provide the heavy lifting services. X-Window is extremely stable and as thoroughly tested a piece of software as anything out there. The fundamental design of X-Window has not been changed in over 20 years. Now, this isn't because people are lazy or they just left well enough alone. What it really means is that it was so well designed that it's withstood a lot of revisions, but nothing really major. Your book will talk about the fact that X11, as in the 11th iteration, major release of it, has been that since really since the early the late 80s, early 90s. So it is the absolute most important layer. Above X-Window is the next layer known as a window manager. Now, X-Window itself, as I said, does all this primitive stuff, like digging the hole, if you will, for the foundation. But in order to be a little smarter about it, we should have a layer above it known as a window manager. For example, if you're using Ubuntu and you've got the default GNOME desktop environment involved, you're going to be using a window manager known as Metacity. I know it looks like Metacity, but it really rhymes with the word capacity. And Metacity is just another layer of software, a set of defined calls and styles that end up calling X-Window to actually create a particular window. Note that with X-Window, you could have your windows look a million different ways. You could have different fonts, different thicknesses, different behaviors of windows, etc. But what we do with a window manager is set some standards for consistency. And consistency is really important, obviously. So at that next layer is the window manager. So the window manager decides on all the look and feel issues. And it's as simple as moving from Microsoft Windows to one of these Linux desktop environments to looking at a Mac, and you'll appreciate the difference of what a look and feel means. And it's all down to the devil is in the details. It's the small things about fonts, about how lists drop, about what happens when you do a right click on the mouse versus a standard left click, etc. The window manager, like Metacity, calls Xwindow to perform all those basic operations. Now, there are lots of other window managers built on top of Xwindow. In this last bullet here, Metacity, KWin is what the KDE desktop in Kubuntu, and a lot of others look at. And I'm going to ask you, actually, as part of this week's assignment, to go look up some other window managers, get some screenshots, and find out a little bit about that other piece of the world. Okay, finally, what we found really in the early to mid 90s, I would say, is that it's nice to have a window manager and that things look, consistent if you're using the same window manager interface like Metacity or KDE or TWM or UWM. You'll certainly come across these as you do some research. But even more importantly is the top layer known as a desktop environment, which really intends to pull all of this together to make a very uniform and consistent experience. And so in desktop environments, we talk about things like, what does the main application menu look like? What are the shortcut keys or operations for moving data between windows? The simple fact that you can be in a word processor or a web browser and select text and be able to copy it and move it over is an example of what a desktop environment gives you. The consistency of all of the applications and the standards for how they look and feel and really behave and interact with each other is what a desktop environment does. What file manager application it uses, for example. And again, a well-defined, a well-designed desktop environment is going to be extremely consistent. Now, things like GNOME and KDE are very mature. They're very heavily worked on, heavily reviewed. There is a community consensus on how they look and behave between one version and the next. And so what this lets us have is a very consistent look and feel, behavior, and experience across platforms. And this is, of course, is really, really important to users. Users don't want to have to learn or look for things being in different places from one environment to the next. So really the desktop environment is, we can see this at the top, is the actual user's view and the user's experience, if you will, for the graphic interface. So that, again, it provides a uniform experience, it standardizes interactions, sets colors and fonts, etc., and there's a couple of examples. So to sum this up, the implications of all of this are pretty profound, really important things. First is that all GUI environments are decoupled from the hardware. So I can have a GNOME desktop and I can move that same software, that same release of Ubuntu, I can move it from an old Pentium 4 system and move it onto a Core Duo platform, or I can move it onto, even it's still being supported on some of the PowerPC, the old Motorola chipset that the Macs ran. All of this can be run without any consideration about changing the higher layers based on how the hardware changes. So very important stuff. These standards also promote uniformity and extensibility. And by extensibility, I'm really talking about some of these the things in this very last bullet on this screen, which is that we can have hundreds and hundreds of different add-ons and plugins that can exist and operate against the same code base. So if you start looking around in GNOME, for example, you'll find that there are plugins for building menus or icon widgets across the bottom of the screen that look very Mac-like, like the Mac's dock. In fact, Docky is the name of one of them. The fact, of course, it's obvious that all of this stuff is open source. That means that anybody out there who doesn't like the existing window manager or an existing desktop, you can go program your own if you're a programmer, if you're interested. All of the intellectual property is available. This is really one of the main reasons this whole GUI environment is why Linux has been accepted at the desktop level and is really starting to give some of the other platforms like Mac and Windows a run for their money. It's still a small market share, but it's growing all the time, and it's absolutely free. So I hope this